Okay, in this video I'm going to talk about the Nagel point of a triangle. So we have a triangle, and we consider the excircles of this triangle. So there is, like in a triangle, there is an incircle that is inscribed circle that touches all sides from the inside of this triangle, and there are three excircles. So the circles that touches all three lines containing the sides of the triangle, but only one line and two extensions of the line. So like like all three of them lie outside of the triangle. So like this. So I'm not going to draw the whole circle style, like there is too little space on this picture. But so the point is that all this circle, they touch the lines containing the sides of the triangle. So and so we take these tangency points of this 3x circle with the sides of the triangle as opposed to the extensions of the sides, and we connect them to the opposite vertex of the triangle. So like this, and like this. And it turns out that these three lines intersect at a single point, and this point is called the Nagel point of the triangle. So let me denote the triangle as A, B, C. It's better to put A here. And then denote the tangency points as TA, prime, TB prime, because like it's to indicate that it's the tangency point of an excircle, not of an incircle. So and TC prime. And so the theorem says that ATA prime, BTB prime, and CTC prime intersect at a single point. So for the incircle, for the tangency points of the incircle, these lines also intersect at a single point, and I proved this in the previous video, and that was like the point of intersection was called the Jirgon point of this triangle. And for the excircles, for the tangency points of the excircles, so this ATA, BTB, and CTC, so intersect at a single point, and this point is called, so which is called the Nagel point of the triangle ABC. Okay. So to prove this, we'll need some property that I actually also proved in one of the previous videos. So the property that we will need is the length that connects the length of the tangency, like the length of this tangent, basically from the vertices to these tangency points, these segments. Yeah, so we will show now that I will not give the full proof, but I will show that this tangent basically, so ATB prime is equal to this one. So and for the other tangents it's symmetrically also the same is true. So let me remind what I proved in one of the previous videos. So if we have an incircle and an excircle, so incircle and excircle, then this tangent from the vertex to the tangency point of the excircle is equal to this segment. So this is B, this is TB, and this is TB prime. And so it turns out that ATB is equal to so ATB prime is equal to CTB. Well, and symmetrically also, like ATB is equal to CTB prime, of course. So okay, let me to show it more clearly, let me highlight these two segments in blue. So these two segments are, well, on the picture they are not very equal, but they are equal. So these two segments are equal to each other. Yeah, and so if you go here, so like notice now that like if we consider now all the so the tangent, now if this point is T, so T, this is TA, the tangency point of the incircle is this side, so this segment is also equal. So CTB, so this is also equal to CTA, because the tangents from the same point to the same circle, they are always equal to each other. So these two tangents are equal. But then applying the same property as this to another excircle, if we have here another excircle, this is the point TA prime. So then this segment similarly should be equal to this segment, right? So this segment would be equal to B TA prime. So yeah, so these two segments, so finally this segment and this segment are equal to each other. ATB prime and BTA prime. So like I showed here on this picture, these two segments. And so the other segments similarly. So like let me show them here on this picture. So this segment is equal to this segment, then this segment is equal to this segment, and this segment is equal to this segment. So now, because of these equalities, so let's now denote these segments by, so the blue one let's denote by x, the yellow let's denote by y, and the green one let's denote by z. So now we can write the Cheva's theorem, right? So Cheva's theorem is a criterion, exactly the criterion one, and the three segments or three lines connecting the vertices of the triangle to the points on the opposite sides or extensions of the sides intersect at a single point. So the Cheva's theorem, so we write so by Cheva's theorem we need to prove, that these three lines intersect at a single point. We need to prove that the product of the ratios, so b ta prime, so b ta prime. I'm not going to write the vectors because all the points are on the sides and not on the extensions of the sides, so the vectors are not very useful. Over ta prime c multiplied by ctb prime over tb prime a multiplied by a tc prime over tc prime b. So we need to prove that this is equal to 1 by Cheva's theorem. If we prove that this is equal to 1, then these three lines would intersect at a single point. So what is this actually equal to? So we write, and the Cheva's theorem, also look one of the previous videos, I proved the Cheva's theorem in one of the previous videos. So bta prime, this is x, this blue segment, then ta prime c, this is that. So basically I replace all these segments with the letters. So x over z, so this. Now what we have here, ctb prime over t prime b, so y, this segment over this segment, so y over x. And the third ratio is this over this, so it's z over y. So that over y. And now we see that x cancel each other, y cancel each other, and z cancel each other. And what remains is 1. And so by by Cheva's theorem, it's not yet by Cheva's theorem, we were just going to apply the Cheva's theorem, but now the conclusion is by Cheva's theorem. So now this implies by Cheva's theorem this implies that a ta prime b tb prime and c tc prime intersect single point. And this concludes the proof. That's it for this video.